Hello, everybody, and welcome to what is hopefully going to be the first of many Skew-T videos. This is actually going to be the first of many Skew-T videos. I don't know where hopefully came from. My name is Chris Sanner, and I am going to be leading you through the bulk of this lesson here on Titan U. And today, this very first video, we're actually just going to take a very basic look at what a Skew-T is doing. I mean, this is the very basics. We're going to introduce temperature, dew point, winds with height. We're going to introduce actually how to read this on a very basic level. You won't learn all the nitty-gritty stuff just yet. That's for future lessons. So let's get to it. Here's my handy-dandy cursor. Now, we're going to forget about this part over here. We're going to forget about all this and all of this. I'm using a Mac, so you can see my cursor will get really big. It's nice. But we'll forget about all that. We're going to look at this square right here for now. Just this area, okay? So first off, what are we looking at? From here over the bottom, this is from left to right your temperatures, okay? And see here is 0 Celsius. These are denoted in Celsius, and this is 0 Celsius, which is freezing. And as you can see, this blue line goes up and to the right. It skews up and to the right, hence the name Skew-T. We'll get to all these other lines in future lessons, but just these lines right here are your temperatures as you go up with height, okay? Here you have a green line and you have a red line. These are pretty universal. Almost always your red line is going to be to the right of the green line unless there is just a very, very special meteorological circumstance, but even still they're going to be together most likely. Won't be any real discernible separation. So anyways, the red line is your temperature. The green line is your dew point. And as you can see, they're going up. And yes, the temperature is falling with height and the dew point is as well in this example. Typically, you will see the temperature fall with height like this. When it's falling from bottom right to the top left, that means it is actually falling with height. Again, these are your temperatures and yeah. So again, the best way to put this is you have on the Sharpie soundings, you have on the left side, you have these are millibars, and we're going up with height on these from 1,000 millibars, which is the surface. At least here in Oklahoma, it is the surface. And from there, you have that all the way up to 850, 700, 500, 3,000, or 300, 200, 100, not 3,000. 3,000 millibars would be below the Earth's crust. But anyways, from there, that's a very basic overview of the temperature and dew points. There's you have temperatures again on the bottom. You have the height right here. You hear us talking about like 500 millibar jet streaks. Well, it's up in this area. So anyways, here on the right side of this window, you have what are wind barbs. I'm assuming at this point, if you're interested in Skew-Ts, you know what wind barbs are. And these are showing winds with height in the atmosphere all the way from the surface here, which, you see a south wind at 10 knots. These are denoted in knots, by the way, all the way up to past 200 millibars, where you have a nice 80-mile-per-hour wind way up there in the way upper atmosphere. And you also have, you have 120 here, 135. So you can see as you go up in the atmosphere, this is your wind. Very simple. The best way to put this is that on the very basic scale, that's what you're reading. If you know what you're looking for, oftentimes those three things I just talked about are the only three things you really need to look for, and the rest just kind of falls into place. But again, there's going to be future lessons. We're going to talk about CAPE. We're going to talk about what this dotted line means, what this blue line means, what these green line means. We're going to talk about all that. We're going to talk about what this bugger is right here, LCL, LFC, EL. We're going to talk about all that, and it's going to be a lot of fun. So in the future, you're going to find out exactly how to read a Skew-T. You're going to become a Skew-T master. You're even going to learn how to read hodographs. You're going to learn what this little effective layer STP with the EF scale means. You're going to learn all of that. It's going to be fun, all these indices. So in future lessons, you're going to learn that. But for now, I think you have a good idea about what the Skew-T is doing here. You have, again, the best way to put it, temperatures here on the bottom, height of the atmosphere going up. So this is a 2D picture of the atmosphere with height. You have temperature in the red, dew point in the green. and you have your winds. That's the very basic of the Skew-T. That's, just the very basics of how to read it. Again, we'll have more lessons on this in the future. I hope this very brief overview is of help to you, and we will see you on the next lesson, and we will break down the LCL, we'll break down the LFC, EL, we'll break down all those fun things. So, until then, I hope you have a great day, and I hope you've learned something. So, we'll see you next time. And one final note, I have to pass this along. If you want to check these out in real time, check out pivotalweather.com. They're friends of ours. It's a great modeling site, and they have these Sharpie soundings. They are incredible. Seriously, pivotalweather.com, your home for weather models. Check them out. Make it happen. Peace. Hello, everybody, and welcome to the second video in the Skew-T series here on Titan U. This is the introductory version of the Skew-T series. Basically, what we're doing with this series is introducing you to basic concepts of the Skew-T chart, how they work, and basically trying, the goal of this is to try to get you a very hands-on, layman's term kind of approach to this, how you could work your way around these and it makes sense. So, anyways, that's the hope of this. We're not going to dive too deep into the science aspect of many of the terms we're going to say, so some of them will go above your head, etc. Look them up if you don't know. We're going to try to add a bunch of these in the glossary and such too as well to really make this worthwhile. So anyways, with that said, if you haven't checked out the first lesson, you should do so. It goes over a lot of the basics, including temperature, dew point, how to look at how the chart works, what the basic setup of it is. So you should check that out, and it'll completely catch you up. Now, with that said, the other thing I want to say, and get out of the way here at the very top, pivotalweather.com, that's where we pulled this sounding from. It's a forecast models website. You really want to check it out. Trust me, it is an amazing experience. We're actually going to have a series on this, or perhaps as you watch this, we have a series on this, of course, on model data and how to read it. So that's something you should totally check out. With that said, we're going to get started by me bringing in the handy dandy mouse again. Whoosh, there it is. I know everybody, the sound effects, very high quality stuff. So anyways, we're going to start our journey today. We're going to look at the LCL, the LFC, and the equilibrium level. Those are the three things we're really going to concentrate on in this video. Now, to do that, we're going to have to explain a few other concepts and ideas, and it's going to be a lot of fun, so buckle up. First thing is first, we're going to talk about the LCL. Now, before we find the LCL, we actually need to define what LCL is. What do we mean by that? Well, first off, LCL is short for lifted condensation level. The formal definition of the LCL is it's the height at which the relative humidity of an air parcel reaches 100%, aka saturated, when it's cooled by dry adiabatic lifting. Why is this important? When a parcel of air is saturated at 100% and then is lifted beyond the LCL, it will begin to condense into clouds. The LCL, thus, is a good measure of how high cloud bases are going to be, or how low, depending on your perspective, are going to be during a typical surface-based severe weather, thunderstorm event during the spring and summer. So basically, the LCL is going to denote your cloud basis. So let's take a look at how to find this on a Skew-T. If you don't have it, I guess the best way to put it, if you don't have it labeled this conveniently, if you're using a Sharpie sounding like this, you don't have to do this because it's already there. But let's take a look. You start with your temperature, and you then make it rise, which again, like this, through the atmosphere at a dry adiabatic rate, which means you just simply draw a line parallel to the nearest dry adiabatic line, and you do it like so, and let's just stop it right there because there's no need to go further. Then, with your dew point, you raise it at the parallel to the nearest mixing ratio line, and you just raise it parallel to that like so. Now, where those two lines intersect, and again, I'll draw it like this and draw it like this, you see they intersect somewhere in here in your imagination. That is the LCL, and bam, there's your LCL. And so at that point, you will have cloud bases lower, or that's where your cloud bases are. The lower your temperature dew point spread, that 77, 74, see how close those are, the lower your LCL is going to be. Generally, the lower your cloud bases are because your environment is more saturated from the get-go. So with that said, you have that happen. Another cool thing about the LCL basically is that, this is a really big figure for tornadoes. The lower your LCL, the better your chance of having a tornado if all the other conditions are right, because it's a lot easier to get tornadoes at lower cloud-based levels than higher cloud-based levels. So anyways, we'll move beyond that. Our tornado forecasting course is totally coming as well, or is here. It's available on Titan U, or it will be available either way. So let's now take a look at the LFC. We're going to take a look at that, but to do that, we got to take a look at a couple of other items on the list first. The first one is your moist adiabatic lapse rate. When air is saturated, it doesn't cool as fast as its altitude increases because it is saturated. This is because the latent heat released when water condenses, it slows the rate at which air will cool. This lapse rate actually varies strongly by temperature, but we'll get into these two here in just a second, or we'll get into this, but this is a line of moist adiabatic lapse rate, and actually your temperature starting here about 500 millibars is moist adiabatic as well. And that's just basically a very simple parcel theory, but very cool anyways. So that's your moist adiabatic lapse rate. They're actually not labeled on this chart, but that's generally the shape of them, I guess, is the best layman's term way to put it. The parcel lapse rate, which is this dotted line, basically it shows the temperature path of a parcel, the temperature path a parcel would take if it was raised from the surface or planetary boundary layer / PBL. To do this, you first follow the dry adiabatic lapse rate until you have saturation, aka the LCL, and then you will see the parcel follow the moist adiabatic lapse rate because the air is then saturated. This path allows us to find things like CAPE, convective inhibition, and other thermodynamic indices. So, you see, again, it's something like this to the LCL, then it will rise up. That's your surface-based CAPE parameter, mean layer, mixed layer, you have all that fun stuff. We'll get into all those things later, but basically that is your parcel. That is your surface parcel. That's the path it's taking. That's how much inhibition you have, etc., etc., etc. So with that said, we're going to move on to this little guy, the LFC. Now let's start talking about the LFC and how to find it, because we are going to totally do it. The first thing you need to know is the LFC is short for the level of free convection. This is the altitude in the atmosphere where the temperature of the environment decreases faster than the moist adiabatic lapse rate of a saturated air parcel at that same level. In short, this is when things go boom in the atmosphere. Finding the LFC is simple, and you can cheat. There is a short way and then there is a long way. The short way involves you finding the LCL and then finding the LFC, or you can just start from the LCL. And basically from the LCL, you would lift the parcel at the moist adiabatic lapse rate until it crosses the temperature line. And at that point, that is your LFC. From there, it will rise your air parcel along the moist adiabatic lapse rate until you reach the equilibrium level. And we're just going to go ahead and introduce that as well. The equilibrium level is the height at which a rising parcel of air is the same temperature as the rest of the environment. Or to put more bluntly, this is when unstable air becomes stable again. This is oftentimes, in practical sense, where the anvils of storms are forming. Now let's take a look at both of those. This is the LFC, this is the EL. So at that point, this is where your anvils will be forming up here. Your storms will be going boom completely right here. Now let's start basically at the LCL. And we got to start it, though, from a surface-based parcel. So, you rise this up, you meet the mixing ratio line somewhere in here, and then it goes moist adiabatic. At that point, you start it up, and you kind of go with the moist adiabatic at that point. and it crosses the temperature line somewhere in here, and thus that is your LFC. That's where your air parcel is going to keep rising because it's warmer than the air surrounding it, and it is not coming back. No, Sally, it is not coming back. It's going all the way up to the equilibrium level, which is up here. This is the tropopause, which is the end of all things surface. But anyways, that's where your anvils will start forming. It's an incredible sight, incredible dynamics. So that's your LFC. That's your equilibrium level. That's your LCL. That's only 3 parts. Look at all this stuff we can talk about still, and we're going to talk about it. But, and not to mention hodographs. I mean, we got hodographs to talk about still. There's all kinds of stuff to talk about. But at this point, I hope you have a good idea about A, what all the rest of these crazy lines mean, and also B, about cloud-based levels, about when things go boom in the atmosphere, and about when unstable things become stable again. That's the best way to put all 3 of those. So, until next time, I hope you enjoyed this video, and I can't wait to get more of these out there. We've got a lot more to cover. We're going to cover CAPE. We're also going to cover a few of these suckers down here, and we're also going to cover, we're going to cover of all this in a very general and broad sense. We won't go into too much detail about all of them because that's crazy and would take hours. But we're going to go into detail about some of them and really just kind of give a why is this important for severe weather kind of approach to a lot of these down here. So anyways, until next time, study up, enjoy looking at Skew-Ts, and kind of having a better idea about what's going on, and we'll see you next. Well, welcome everybody to the 3rd lesson in our Skew-T series. If you missed the first couple, you've missed a couple of important lessons. You find out how this chart is laid out, and the last lesson we actually took a look at the LCL, LFC, and equilibrium level. Those were fun. Today we're actually going to take a look at a few of these down here. We're going to take a look at surface-based CAPE, mixed layer CAPE, and most unstable CAPE. These are fun things to talk about, and we're certainly going to do that here in this lesson, where we basically break down how each of these work and what to look for with each. So this is a sounding from May 16th of this past spring in central Oklahoma, aka the National Weather Service in Norman. They launched this balloon in the middle of the afternoon. This was the 1 p.m. sounding /18Z. This shows, again, this is all things you should be familiar with at this point. It shows, good wind shear. Here's your temperature profile. Shows a little bit of a cap here with temperature and dew point. And of course you could find your LCL if you wanted to, etc. I mean, you can do all that. So all that's possible. But we're going to take a look today at the instability. Now, first things first, let's take a look. Let's ask ourselves, what is surface-based instability? What is mixed layer instability, etc.? Well, surface-based CAPE, or SBCAPE, is simply calculated by lifting a surface parcel of air upwards in the atmosphere. Basically, the 76/60, that's what we use. This is the literal calculation. You don't go any further. This is exactly how you calculate your surface-based instability, and because of that, you lift it dry adiabatically until you get to the LCL, and then it just takes off moist adiabatically at that point, and that is your surface-based instability. This is the amount of instability you would see realized if an updraft was lifting air from the surface into the atmosphere. Of course, though, this is important to note, surface-based instability rarely is what you see realized during a day, just because of the simple fact most updrafts aren't lifting this into themselves. 76/70 is not what most updrafts are going to end up doing. However, mixed layer CAPE, mean layer CAPE, or just quite simply MLCAPE, it refers to a parcel path which is taken from the average of the temperature and dew point values within the lowest 100 millibars of the atmosphere. This number is almost always smaller than SBCAPE, so it can be really mean in that regard. It can take a lot of your juju out of the atmosphere, as this sounding does actually show. This is probably more realistic about what kind of instability is being realized with storms. This is because air rises, and as it rises, it mixes with air surrounding it, and so storms are typically going to be ingesting this air versus a pure surface-based air parcel. And the reason for this is simple. Look at this, 76 over 70, but look how fast the dew point drops off just over the surface. It gets very dry in this sounding. And again, the temperature also, same thing. But you see a lot of cooling and a lot of drying. It's actually temperature from the surface is almost cooling dry adiabatically. And from there, I mean, you can see that's a big problem. Just above the surface, it's cool and it's dry. I mean, that's not a very unstable sounding. And then, you go up here and you have a massive cap actually in place as well. And for the record, it took a lot of work to get from here to storms on this day. For sure in OUN. There was a lot of clouds and such. This was just not a good day in Central Oklahoma at the time. And as you can see, your surface-based CAPE, it's 3523. That's because if you lift a parcel from the surface, it's quite unstable. However, at mixed layer, it's 716 with 151 of that being sin. I mean, that's and we'll talk about sin. We'll talk about that in the cap at some point in the future. But if you take a look, I mean, it's dry. When you take a look and you start a ML mean layer average parcel, I mean, you're going to end up somewhere up in here, and then you just start lifting it. I mean, it's not much CAPE. And so that's what happens oftentimes. You'll see storm chasers and weather people really oftentimes. They'll buy into this right here, but the mixed layer CAPE is really what's more important when forecasting for severe thunderstorms, so that's what you're actually seeing realized. SBCAPE produces a lot bigger and meaner numbers for sure. I mean, you can see SBCAPE 6,000, 7,000 sometimes, but then the MLCAPE's like 3,000. And that's because you usually have some dry air. It's cool and dry in parts of the lower atmosphere, and that's what you end up with. MLCAPE is prone to some errors, though. This should be noted. It requires an accurate representation of the atmosphere's lowest 100 millibars versus SBCAPE. So on models and such, they can sometimes get this wrong. So SBCAPE's also useful in that regard. SBCAPE is certainly going to be accurate since you have real-time observational data to go off of. It's kind of easy if you have a reading of, 78 over 71 to lift that parcel and get something, and at least that's right. However, the opposite of this can also be true in the sense that if your surface moist layer is very shallow, this is a very good example of that. SBCAPE will appear huge, but MLCAPE will be a more accurate measure since it takes into account the drier air just above the surface, and this is, you're seeing that right here. So what about most unstable CAPE? Well, MUCAPE is really used for elevated convection scenarios. This is best said as, when there's a surface inversion, or, your storms are based well above the surface, elevating, For example, in this scenario, your most unstable is 3523 because it's taken from the surface. But if this cap were a little bit more, way out here or something, you had this monster surface inversion, your most unstable layer of air would be somewhere up in here, and you would get a more accurate measure of the atmosphere at that point. So this gives you the most unstable parcel of air in the atmosphere, the most unstable CAPE. So there's a couple of ways to do it. One way is that it kind of just calculates from 200 millibars on down, air parcel path, and whichever one's the most, that's your most unstable, and that's what you see used most often. And for the most part, in elevated convective scenarios, this is pretty important, but you can also oftentimes get situations where your most unstable CAPE is taken from, this one's 970 millibars, but, you can get it, taken from 850, but your storms are actually based at, the lifting is at 700 or something crazy like that. It can happen. So regardless, that's the difference between surface base and mixed layer CAPE, mean layer CAPE, etc., or MLCAPE. We're just going to call it MLCAPE. Let's take a look at another sounding from this day at OUN to see what happens a little bit later, just to kind of demonstrate this. Okay, this is the 0Z sounding from May 16th. Again, you see it's May 17th at 0. That's we'll talk about Zulu time another time, but if you don't know what Zulu time is, this is basically just the universal time scale we use in weather, and that's just 5:17 of 0Z, which is basically the evening of the 16th. If you're confused, that's okay. It happens. So anyways, Let's talk about, again, how has the sounding changed? Well, suddenly, again, 71 over or 75 over 71, your surface bass cape, it's just immense. It's 4,000. That's a lot of cape. However, again, your mixed layer cape 2347. That's because if you take a look at, it's a little cool, it's a little drier, but it's nowhere near as warm as 75 over 71 in the lower layer, the atmosphere. And so you see that played out in the mixed layer cape when it's 2347. That's why it's a lower, but that's a more accurate representation of the storm environment that is going on here at Norman. Now, there weren't tornadoes in Norman on this day. They were all along the Red River and west of there, actually some northwest of there too, basically west of Norman. Norman was east of everything for the most part during the day. There is still a little bit of an inversion here in the mixed layer, but nothing that's not being broken by anything worth anything. So, basically, when you're looking at soundings, surface-based cape, I guess the big takeaway from this lesson in the Skew-T soundings is that it's easier to calculate because it's all right here. Mixed layer, models do it for the most part. You can certainly calculate it by hand. This lesson is not teaching you that because A, we're not teaching the math behind it, and B, that's a lot more complex, to put it mildly. But you can kind of see the rough reasoning for why you have less mixed layer cape. You see rapid drying just above the surface, so you have less dew point, but it's still pretty unstable is the best way to put it. If you get over 2,000 mixed layer cape, that's pretty strong instability. It's moderate, I guess, officially classified, and we'll look at those terms in another lesson just all about cape. But in terms of the Skew-T, that's how you look at it. I mean, you see that, and it's pretty easy at that point to then figure out what we're doing with that. So again, pretty simple. Don't overcomplicate this. Your surface space instability, it's useful in some scenarios, but for the most part you want to be using MLCAPE to measure how unstable an atmosphere really is, because that's the more realistic representation. Even though it is prone to some errors, it is a more realistic representation of what a storm is actually going to be dealing with. So until next time, hope you learned something, and we will be back with a couple more lessons on Skew-Ts, so stay right there. Hello again, everybody, and welcome to the fourth lesson in our Skew-T series, and we're basically really hitting on some pretty big issues now, some pretty big topics. We've hit on, just the basic setup of the chart itself, how that works. We've hit on the LCL, LFC, and equilibrium level. We just hit on instability, and today we're going to look at the winds, wind shear, the wind shear parameters. We're going to look at, wind barbs right here. We're going to take a look at those a little bit. We're also going to take a look at these numbers right through here and really get a good idea about what all of this means, because quite honestly, it's something that we should be discussing for sure. So let's just start off by saying, when you're looking at wind shear, it's a very nuanced kind of view. I mean, the first thing I always look at when I load up a Skew-T chart before I look at anything else is actually the wind barbs right here. You can tell a lot just visually looking at them. On this particular sounding from May 16th in the evening, you can see, there is some really good turning and veering with height, but there are a couple areas where you have some backing of winds. And that results in some jankiness over here in the hodograph. It's not what you would expect, For the ideal scenario, you want a hodograph to look something like that, a nice sickle. And that's, you don't have that. It's not an ideal hodograph because you have some backing here at the 500 level, first off, and then you have a little bit here even at the 700 level. And that veer back is just not great. You have veering and then backing. That's what we call veer back. So, right there, the first thing I notice, not the greatest. This actual chart actually shows the storm motion on the Storm Prediction Center website. So you can actually see, because of this, you can actually see the Helicity mapped out right here. So that allows that's a nice feature, and it also allows you to start thinking a little bit about what would happen if the storm turned a little right, because you see it's 222 at 38. You take this at 222 degrees 38 knots, and that's what you end up with right there. Right, follow 40 knots. So yeah, that's your storm motion. Now, if this storm turned really hard right and slowed down, you know, right over here, you would increase your helicity. I mean, imagine how much more space that's taking. So that's just something, that's just a cool little thing. We won't get too far into photographs in this lesson, but that's just a little sampling, you know, of what you would want. We probably are going to do a whole series on photographs eventually. So let's just hold our horses. Another thing to keep in mind, you know, when we're talking about shear stuff, again, it's a nuanced view. We need to be very careful about how we approach it because a lot of these numbers, winds are not constant. Have you ever stepped outside and felt a constant wind? That's not the case. You know, you have an average wind speed and you have gust, etc., and that's the truth all the way up the atmosphere. It's not a constant thing. Winds can suddenly die down. You know, this is something that changes quite rapidly, actually, sometimes. So it's just something to keep in mind. Sometimes you'll end up with dead zones within an environment that you did not realize were there. You thought you had great wind shear and storms don't look sheared at all. I mean, that's happened before. So, I mean, just it's interesting to keep in mind all these things. But let's take a look at it. First thing we're going to look at, this right here. This is helicity. And helicity, let's talk about what is helicity. Well, it's a parameter. It takes into account speed shear, or how much wind increases with height, directional shear, or how much it changes, how much wind changes direction with height, and the strength of low-level winds, which ties directly into the speed and directional shear. The stronger all three of those ingredients are, the more helicity you're going to have. Now, 0 to 3 kilometer helicity is high enough for supercells and even tornadoes at values of over 150. But you're kind of wanting 300 to 400 for the more higher end tornado days. For 0 to 1 kilometer helicity, anything over 100 is fair game for tornadoes. As you work your way up, you get more into this could become a violent tornado kind of environment. Now, keep in mind also, if you're looking at a model forecast chart, sometimes helicity will be completely misleading. You'll see, you know, crazy helicity values in a place like right behind a cold front. That's where tornadoes are never going to happen, almost always. And, you know, that the major turning in the low levels results in a lot more helicity than is actually, you know, it looks a lot more dangerous than it really is. So you got to have some skill in interpreting these values. On this chart in particular, again, this lesson, the goal is not to teach you the mathematics or the how to calculate these too in depth. So we're just going to gloss over that. We're just going to look at what is. The surface to 1 kilometer helicity is 310. Again, anything over 100 is fair game. As you get above that, especially over 300, you can start talking about strong tornadoes, and that's definitely possible. Surface to 3 kilometers is 398. Again, that's in that 350 to 400 range. That's right, or 300 to 400. That's right up there. I mean, that's up there in some very strong range. This is a definite tornado kind of environment. Even though you got some veer backing, the helicity is there. There's plenty of turning in the atmosphere, plenty of shear to make tornadoes in this environment. And you can see it. I mean, you can definitely see it with the southeast winds at the surface, turning to south-southeast 850. You're at south-southwest, or even southwest at 700. You know, at 500, you have that weird backing there, which results in this weird stuff. But still, it's really good shear. So let's take a look down here at the surface to 6 kilometer to surface to 8 kilometer shear. We're not going to really look at the 8 kilometer. We're just going to kind of gloss over that for this one, and also all the rest of the stuff. We're just going to kind of gloss over all that. We're just going to look at surface to 6 kilometer shear, which right here is 56. So what does all of that mean? Well, first off, the shear is basically it's a change in wind from boundary layer to 6 kilometers above ground level. This is simple, and it really does sound like what it is. It's just simply the shear value, how much wind speed changes, or the winds change with height. For 0 to 6 kilometer, we look for values in the in this range of 30 to 35 knots for supercells. Anything below that, storms are going to struggle to get organized. For the big high-end days, 50, 55 knots is what you're looking for. Obviously, again, you got plenty of that on this sounding. It's there. It's, you know, it looks good. Another parameter that's we're not looking at on this one is the effective bulk shear. I look at this all the time on mesoanalysis. I'm a big fan of this one. It's basically the most unstable parcel lifted upwards 40 to 60% to the equilibrium level. So, you know, basically the most unstable parcel up, you know, somewhere up to this point, and that is then your effective bulk shear, where it's taken into account. It's similar to the actual bulk shear, but it tries to account for storm depth, and it's designed to ID both surface-based and elevated supercell environments. Again, for supercells, 25 plus knots is preferred, although 30 plus knots is minimum, is what I kind of look for. So again, the effective bulk shear is really good. In the case where you have elevated convection, you can check actually the bulk shear values for that. So that's your helicity and bulk shear. That's the two things I really look for. One last note on wind. Most soundings these days are showing storm motion vectors for right motion and left motion. As a general rule for me, I tend to say when storms go up, they're going to be more left movers. They're going to have more speed. So 52 knots, that equates almost to 60 miles per hour. And as they hit their stride and turn right, 38 knots. That's oftentimes a little too fast for a storm that's producing a tornado. It seems like oftentimes storms that produce tornadoes will even tend to anchor out a little bit and move a little bit slower, turn a little bit further to the right. Again, that's something that we'll have to talk about in another lesson. We could spend an hour talking about why storms do that. So that's wind shear. It's pretty basic stuff. Again, these are important. Your wind barbs are important. Your hodograph is important, but we really didn't touch on that enough, but we will in a future lesson. And also, helicity, bulk shear, storm motion. So that's your basic look at wind shear. Our next lesson, we are going to talk about all these other indices you see thrown out here. We're going to look at those and how to see them on here and kind of how to read a few things. And yeah, that's going to be a fun time. So join us for the next lesson. We'll be back soon. Hello, everybody, and welcome to the next to the last lesson in this course about reading Skew-Ts. This lesson is going to center on a couple of additional indices that we have not yet touched on. The previous lessons we've touched on how the chart's laid out. We've touched on things like LCL, LFC, equilibrium level. We've touched on instability. We've touched on wind shear. Today we're going to look at some composite indices and really just kind of explain how they're calculated using the visual of a Skew-T. But in general, you don't usually use a Skew-T to calculate these. I mean, from a just layperson standpoint, that's not really what you're doing with it. Your main reason for using these indices because they're already calculated and they're just easy to figure out. So we're going to use the May 16th sounding, the 18Z one, this time once again. And we're going to look at these right here. We're not going to look at left supercell, and we're not going to look at sig hel in this, but we are going to look at the supercell, the sig tor parameters, both effective and fixed. We're going to explain the difference and show it up here. So anyways, let's take a look first off at the supercell composite. What is the supercell composite, you might ask? Well, this parameter, the supercell composite, is designed to detect environments where right-moving cyclonic supercells are most possible. This is used to detect those environments where supercells are just most likely to be seen. The higher value, the more higher chance of a supercell sort of thing. The ingredients for this composite parameter include effective storm relative helicity, the most unstable CAPE, and the effective bulk wind difference. This parameter is designed to show where these three ingredients overlap the most with one another in an environment. The higher values of supercell composite, the more you have potential for supercells just because of this parameter. Not always is this the case. Sometimes you'll have high supercell composite parameter, but in reality, the setup favors a line of storms, etc. So it's used as a tool. If you're going to get discrete storms and you have a high supercell composite parameter, the odds are pretty high you're going to have supercells. Same thing with significant tor, the significant tornado parameter, or sig tor. Same kind of thing. You need supercells before you can get sig tors, at least in this regard. Almost universally you need supercells or just some kind of way to get low-level mesocyclones. If you're not going to get that, you can have all the sig tor in the world. It doesn't matter because you will not have significant tornadoes. Fixed layer sig tor is it's a composite index which takes into account the 0 to 6 kilometer bulk wind difference, the 0 to 1 kilometer storm relative helicity, surface-based CAPE, and the surface LCL. So basically, the fixed layer takes into account a lot of this right here and also goes exactly 6 kilometers up. So it's very much a universal kind of standard in the sense of this is where this is what we're calculating. Fixed layer, it does have its uses. I personally prefer the effective layer SigTor, which we're about to talk about, but fixed layer does have its uses. It really takes into account the surface-based environment, so it's there's uses there. The effective layer SigTor, it is similar to the fixed layer in the sense of that it takes into account a bunch of parameters for tornadoes, but it takes into account different ingredients, which these don't focus so heavily on the surface parcels we just talked about. It doesn't take into account what happens if this parcel right here is lifted up in the atmosphere. It takes into account more the mixed layer, this whole thing. What is the storm ingesting from the surface to the cloud layer? It takes into account the effective storm relativity, the bulk wind difference, the convective inhibition in the lower levels. That's important, and also the mean layer parcel LCL, the MLCL, and not the surface LCL. So it takes into account all those. I personally think it's a better view of the environment and its conduciveness to SigTors given storms that can produce significant tornadoes. Can't say that enough. Anytime you see parameters like that, like these down here, and they're high end, you got to have supercells first. You got to have isolated storms to get supercells, or at least semi-isolated to get powerful supercells. Then you need supercells to really see SigTor enhanced or it fully realized. So they're tools, they're not to be gone off of. Just those values being high doesn't mean anything on their own. You have to have other evidence to support that potential being realized. Okay, the other thing I want to talk about in this lesson are lapse rates. Now, on a visual level, lapse rates are simply put the change in temperature with height in the atmosphere. If you see the temperature falling with height, that is your lapse rates. You can take it from, say, the 850 layer to the 500 layer. There's not much of a change in that. There's a big change from here just above 850 to the 500 layer, but at 850 it's actually not that big of a change. And you see this played out down here. You see these numbers: 7.1 Celsius per kilometer, 6.1, etc. Lapse rates are very important for determining potential for instability during the day, as well as the potential for large hail associated with powerful updrafts. Without strong lapse rates, an environment isn't terribly unstable. Well, what do these numbers mean? What is the number that you're looking for? Well, first off, on the lower end, anything below 6 represents pretty stable conditions. Anything near 9.5, which is dry adiabatic, we've talked about this, it's considered absolutely unstable. In between those is conditionally unstable air, which means with enough moisture and lift, the atmosphere can be unstable. So anyways, that's the very last bit of indices we want to talk about here. The next lesson, we're going to put all this together, look at some Skew-Ts, and assess some environments. Basically the hands-on, let's put this into practice lesson. So that's what many of you have been waiting for, so we're going to do that. So we will see you in the next lesson. Hello everybody, and welcome to the very last Skew-T lesson, at least in this beginning course on reading Skew-Ts. And we're going to be taking a look at 4 different versions of Skew-Ts. We're going to look at 4 different days, and we're going to kind of break down what each of them are saying so we can kind of get a better idea about, how the process for reading these. This first one is from April 22nd this year. It is the 19Z sounding from Amarillo. That is the afternoon sounding. It's 2 o'clock in the spring, actually. So we're going to take a look at this one. First thing I always look at, literally my eye goes right here first, 64 over 54. That's exactly what you're looking at in terms of temperature and dew point. You can see very clearly the moisture is very shallow. Surface dew point's 54. Just above the surface, you're way lower than that. It drops quite dramatically. You also have a capping inversion where it's warmer and drier up in the upper atmosphere. That is very common in the spring. That's your elevated mixed layer. That will happen. And the thing you'll notice is that your surface-based instability down here is 1558, and that's because 64, 54, not bad. But look how much how much cooling and drying takes place just above the surface. Because of that, your mixed layer CAPE as of 19Z is only 322, and look at that that monster cap of minus 248. We're going to have a lesson on the cap eventually that will let you really dig into that, and it'll involve a lot of Skew-T work. And the other thing I look at, at this point, because this is the early part of the afternoon. Those are the things I look at in the early parts of the afternoon for sure. You know, what's the cap doing? How deep is our moisture? In this case, not very deep. You know, what's the odds of us getting some surface warming? There's full sunshine going on here, so you're going to get a little warmer to weaken that cap a little bit. The other thing I look at is the winds, and you can see clearly, you know, pretty decent turning basically from the surface up. But this is kind of dramatic too. You actually see the hodograph does a little bit of a funky thing there. It's not very conducive right now. I mean, as you can see, your surface to 1 kilometer Helicity plus your surface 3 kilometer, very meager right now. It's only 72 and 14. Your 6 kilometer shear is 39, so you do have enough for supercells. But if you're looking for tornadoes, that's not happening. Slow movers though, if you get a storm. I mean, look at this, right motion 14 knots. So that, you know, that's this one. Not much to it. It's an early or mid-afternoon right before storms form, I guess. So it is important, but you know that your environment's not quite there. Let's go to the next one. This one is from May the 6th at 19Z. This is at the same time, just a couple weeks later. I mean, look how different that that looks. So this environment, 73 over 69, is obviously a lot bigger in terms of that. In terms of what it's offering, very moist atmosphere. You can see actually pretty saturated all the way up to what used to be a cap. There used to be a cap here in the morning sounding. There was a little bit of a cap. But also, you know, again, 3,500 surface cape for obvious reasons. Your mixed layer cape's 1409. There is a little bit of drying, a little bit of cooling. So, you know, you take all that into account on what the storm's ingesting. Your LCLs are reasonable, you know, pretty reasonable. Your MLCL mixed layer, it's up in here. So that's about where your cloud bases are, just below the 850 level. And then you just take a look at, you know, you take a look at the Helicity, 197 and 213. Pretty good. 6 kilometer shear, 41. So you got plenty for supercells on this, on the very basic level. You know, we've looked at this and we looked at this. I mean, that's basically the simple point is when you're looking at Skew-Ts, especially from a chasing perspective, you really, I mean, you can go really deep if you want to, but there's only a few things you really need to look at to really get a good idea about what kind of day you're facing. You see here, this photograph's got all kinds of scrunched up stuff here. That's because of weakening winds with height. That's what will cause that. You also have some veering with height. You know, you have it back. You have backing with height. Excuse me. You have it veering, then it backs, then it veers again, then it backs. So this photograph right here, not the very greatest. Your low-level environment's good, but you know, everything on the upper levels, it's not the greatest. Very scrunched up, lots of twisty lines. You, like I said in the wind shear, you really want a photograph that looks like that for the very most violent kind of days. But what happens here is that you actually have an outflow boundary very near this location, and when you take into account the even further back low-level winds and such, you actually have a much more impressive surface to 1 kilometer Helicity values. I mean, you're already at 197. That's good enough for tornadoes. Anything over 100, you're game on. So, you know, you can see, you know, the overall environment's not the greatest for big storm organization, but it is good enough for tornadoes for sure, and supercells. So you don't need an ideal scenario to get tornadoes and supercells. You simply need wind shear and instability that's sufficient to get a storm to do its thing. You won't get the ideal, you know, crazy cyclonic type of action with this hodograph, and you certainly didn't on this day, even though these storms did end up being prolific tornado producers at different times. So that's just one thing to look at. You know, you got to keep an eye on all this stuff. It's very important. Again, let's take a look. I mean, you see the Supercell Composites 18.8, your Sig Tours 1.73.1. We really didn't go into what's good here, but anything anything over 2, I kind of get excited about. Anything below that, and it's there, but it's not, you know, it's not extreme. So that's something to keep in mind. So let's take a look at the next one. This one is from Fort Worth on May the 10th. This is actually the May 11th 0Z sounding, which is May the 10th at 7 p.m. This day was a very messy storm day. There was just a ton of storms, and actually here at Fort Worth, as of 0Z, you actually had some surface stabilization here a little bit, because the surface temp, you know, 75 over 71, it was a little bit higher. Getting that to lift up through the atmosphere was, you know, it takes a little bit more. So You have 75 over 71. Some real cooling and drying with height, of course. That leads to a little bit lower mixed layer CAPE. Also, your MLCL is, it's quite high, actually. It's up in here, which, when you dry a parcel dry adiabatically and then go along the mixing ratio for the dew point with height, that's where you end up with. And then your LFC is right up here. It's actually, I guess we're looking right in here, and your LFC is right here. And then it just takes off. But it's only 1346. So it's not, 2800 surface CAPE, 1300 mixed layers. That's enough to do some damage for sure. And again, you see the photograph. It's really big here in the lower levels. There's a lot of wind shear. You can see it here. But again, it's not the most ideal scenario above. You get some weakening and backing of winds aloft. That doesn't lead to ideal scenarios for sure in terms of storm organization. But this day did produce a very weak but large tornado. Believe it or not, just north of Dallas-Fort Worth by a couple of hours, or by an hour. It was about an hour, about 30, 40, 50 miles up I-35. This environment not conducive for strong tornadoes, it doesn't look like. When you look at it, it's not the strong tornado environment you typically look at, but this is an environment that did yield a few tornadoes and large hail and some damaging winds. So, again, you have your Supercell Composites, 13.8. That's pretty good. You have your effective layer STP at 0.8 and fixed layer at 4.3. And some decent lapse rates, but look at this, the 3 to 6 kilometer lapse rate's actually below 6. That's not very good. That's not the most unstable atmosphere for sure. You didn't get the biggest hail sizes on this day because of that, but at least at this point and later, you did have a little bit of warming. So anyways, let's take a look at one final sounding. This one is from May the 10th at 18Z. This is actually earlier in the day compared to this one. Look how much that changes. You go from 71 at 0Z, the dew point, but it's mixed out 67 here. Look how much more saturated this is. Again, you don't have much surface CAPE because look how much warmer it is aloft compared to the surface, 68 over 67. That's a very cold kind of sounding. However, I will say your shear is a lot better earlier in the day. Your shear got a lot worse through the day. That's actually a sign that you have a storm leaving you. But, you can't get tornadoes if you have a huge surface inversion like this. It's not very easy to do. But, you have cloud bases super low to the ground with this sort of a sounding. But this is a sounding that isn't yielding much in terms of composites. The lapse rates are just absolutely not there. Your surface to 3 kilometer lapse rate's 5.2. That's not even good enough for anything. You cannot get much out of that. So, again, you see it. You see some cooling right in through here, warming down in the lower level. So this is becoming more unstable, but at the same time, it's good wind shear, but the thermodynamics over here are not that good. You're not going to end up with a huge severe thunderstorm event. So basically, when looking through soundings, the first thing I always do, again, is I just check the surface. I check all this right here. Basically anything below 700, then I'll probably skip over here to the shear and the hodograph, and then I'll dig into the instability, the shear composite parameters, and then all this stuff right here. This day, look at this. Look at the 3 to 6 kilometer lapse rates. 8. That's really unstable. This day is good for big hail for sure. So, again, that's just the basic workflow. It's just a demonstrative purpose. There's several different ways you can attack these things. That's kind of how I attack them. There's no right way, no wrong way to do this. Well, actually, there are plenty of wrong ways, but there are plenty of right ways, I guess is the best way to put it. There's a lot of ways to do this. There's a lot of ways you could do it and be completely dead wrong. So, again, pretty simple. Skew-Ts on the surface look really complicated, but they're actually pretty simple to break down and dissect. And if you want to chase storms, or if you just want to be more prepared and more informed about what's going on in the atmosphere, these are essential to really getting a good read about what's going on. So, with that said, I hope you learned something in this course. We will have many more courses on Skew-Ts in the future, more advanced stuff. Also, we'll be incorporating these into other courses, especially now that we have a Skew-T course done. So, this course is mightily important. Thank you for watching, thank you for reading, and thank you for participating. And we will see you on another course.